Okay, good morning. So this is a course, Theory of Discrete Algorithms. And as you can see, in this course, the whole course will be videotaped, will be recorded. Yeah, so actually, I'm getting nervous, but of course, you don't have to be. Okay, good. So this is first class. So I'd like to give you some general issues before getting into real contents of the course. Okay. So number one is name of the course. This is a formal name, but I'd like to use another different name for this class. Namely, this is Introduction to Contemporary Algorithms. So I prefer this name for the class because it describes the course much better than theory. This a very general name. It's much more specific. Okay. So my name is Iwama, and my office is room 234 in this building. So new number 7 building. Okay. The second issue, number 2, as I already said, this course is and will be recorded, videotaped, and it's going to and the whole course will be going to you're gonna be one of the online courses provided by Kyoto University OCW. OCW stands for Open Courseware. So, this course, theoretically speaking, this course can go to all over the world through internet. Okay? So that's why I'm getting nervous. Our cameraman is Mr. Kazuo Fujioka. Thank you very much for your great job. I hope. Okay. And I'm not very sure if I need your formal approval for making a video, but I hope there are no big objections. So, is anybody strongly against recording of the course? Okay. Thank you very much. Okay. Number 3, this is important. So probably, if you go to, for example, North America, then the teachers spend a lot of time for this third issue, namely grading. Prerequisite or office hours, and so on so forth. The most important part of the general issues. Okay, so as I said, if you go to North America, for example, then the teacher tend to spend a lot of time for explaining these kind of things. So that means over there, the course is kind of contracts between teachers and students. So they are very nervous about this kind of things. But of course, this is Japan, and in Japan, traditionally, of course, the things are changing. So especially for undergraduate courses, we are now introducing the same system, somewhat same system as US. Namely, we have a lot of details about how to grade, how to give your score, and so on and so forth. This week's will be midterm, and this will be problem sets, and so on and so forth. But this is a graduate course, so I'd like to take more, traditional Japanese style that is sort of easygoing. Okay, so this is Japanese style class. That means okay. So grading is only one final. Only one final test, final exam, and furthermore, this is a take-home test. So you don't have to worry about that. This is just take-home test. So the idea is this. Maybe 2 or 3 weeks before the end of the course, so it's in July, I'll put a problem set on my webpage. So just you have to you solve those problems and submit your answer to me. That's it. Then I'll be grading that you answer, and that's your grade, that's your score. So it's very easy. You don't have to worry about at all. Okay, and we have no prerequisites, but I'm assuming that you have some kind of experience of programming. Just programming. So I hope all of you have maybe just small experience of writing some programs, or maybe reading some programs. Okay, that's it. That's fine. And maybe I'm gonna be using this kind of expression. Big O notation, what we call big O notation, big O of n squared, something like this. So I gonna use frequently this kind of notation. So if you meet this notation for the first time, then it might be a good idea to read some the introductory algorithm books. So for example, if you go to a library, then there are many textbooks for basic algorithms. Then you immediately come across this notation, big O notation. And the idea is this is n square, approximately n square. So it's not difficult. Yeah, it's not difficult at all. Okay. So we don't have any basically no prerequisites. And office hours, you're always welcome. Yeah, as if I am there, I'm pretty much there, so no problem. Okay. So this is grading, And no handouts. No handouts, no textbooks. Actually, there is a textbook. So this is a book of myself, and actually, the title of this book is very interesting. Algorithm science. It's interesting. Algorithm science. Super introduction. Introduction from exit. This is really, really, funny title. Of course, it's just a Japanese title is here, but its English translation is introduction from exit. Yeah, it's a very funny name. Yeah, but anyway, and actually, this book includes almost everything of this course, but unfortunately, this is written in Japanese. So if you read Japanese, then it might be a good idea to buy one. And if you don't read Japanese, then that's fine. No, completely no problem. Okay. So this is a lecture completely using blackboard, and of course, I'm writing very slowly. I'm going slowly, so taking note should be easy. So don't worry about that. Okay. So maybe this is up to now. This is a kind of general information of this course. Any questions so far? No? Okay, good. Okay, now I'm gradually getting into contents of this course. So number 4 is the goals. Okay, what is the goals of the course? That is exactly contemporary algorithms. So what is the contemporary algorithms? This whiteboard is sometimes also good. Okay, contemporary algorithms. What is contemporary algorithms? To explain contemporary algorithms, maybe it's a good idea to explain what is not contemporary algorithm. Okay, not contemporary means some kind of older style or traditional algorithms. So this is opposite. It's old style. Or traditional. Algorithms. Okay. So what is the standard? So if you attend, for example, some basic algorithm course, then what would you study? Then maybe it's a first thing you study about the algorithms is this. Algorithms should be correct. Okay, this is the most basic thing about algorithms or programs. Okay, when you write programs, when you design algorithms, it should be correct. It should give you a correct answers. That's the most important thing. If it's not correct, if it doesn't give you any correct answer, then it's garbage. Okay, it's nothing. Well, this is the most important thing about algorithms. Okay. The next thing is should be efficient. Efficient. Maybe both in time and space. So that is why here, exactly here, this notation comes in. Okay. So for example, you say that my algorithm runs in order n square time. That means approximately, of course, it's totally impossible to measure the computation time exactly. So that's why we use that big notation. That means my program, my algorithm runs in approximately order and approximately n square time. That means something like 10 times n square time, or maybe 5 times n square time, but we just ignore coefficient. Okay? So that's why that is a big O notation comes in. So this is a kind of a traditional style of algorithms. They should be correct. They should give you a correct answer, and they should be efficient. Okay, then what is new algorithms? New algorithms. Okay, a little bit different from traditional one. The first thing is they may not be they may not be correct. Okay? So now we have no agreement. We have no guarantee that your algorithm will give you correct answers. Wow. That's a big difference, from the traditional algorithms. May not be absolutely correct. Why? Why? There are several reasons. The first reason is, okay, in order to get the correct answer, of course, you need the correct inputs, right? Correct inputs. If you can't get correct inputs, then of course it's totally impossible, to calculate, to compute the correct answer. So, recently in the world of new algorithms, sometimes we can get partial information. Partial information for the input. Okay? So sometimes it's impossible to get the whole input, only partial information about our input. I'll give you some example. Just consider algorithms for stock trading. Yeah, stock trading. What is input? Input is a sequence of prices of stocks. So company A, company B, company C. Okay. So price AI, price BI, price CI. this day I. Day I. Okay? Day I plus 1, A sub I plus 1, B sub I plus 1, C sub I plus 1, and so on and so forth. This input. What is output? Output of your algorithm is an action, profitable action. So for example, day I, no action, nothing. So you don't buy or sell your stocks. Okay? Day I plus 1, maybe buy 20 stocks of company A. Okay? So this is output. Output means your action. But of course, why that you have to buy 20 stocks of company A? Because you don't have any information, or theoretically speaking. Of course, you can guess. You can guess the future prices, but theoretically speaking, you have no information about the future prices of the stocks, right? So you have to make a decision. You have to make decision only using input up to the date. Okay? No information, no inputs, no information about the future input. That is what I'm saying, that the partial information for the input. Okay? Although you don't have future information about the input, you still have to seek profitable actions. That is the goal of your stock trading algorithm. Okay? That's why it's theoretically impossible to get correct answer, correct outputs, right? Unless you are God. Okay. Or it is theoretically possible. It is theoretically possible to get absolutely correct answers, but it would need too much time. So this is another reason why you can't get the correct answer. For example, suppose that you have to compute some difficult problem. Then if you try to get the correct answer, your computation time might be 3 years. 3 years is totally impossible. Okay? So that in that case, maybe you need to give up correct answers. Then what would you want to have? Approximation, of course. Approximated answers. And what about the efficiency? What about the efficiency of your algorithms? Okay. Of course, time and space are important, but recently we have some other things that are important for efficiency. For example, I'd say more. Some cases, there are things that are more important, even more important than time or space. For example, communications. It means sometimes there are two parties, Alice and Bob. I don't know why they use Alice and Bob, but this is our practice. We usually use Alice and Bob for two parties. for some computation, they need communications. Then, of course, the amount of communication is very, very important for efficient computation, because, of course, communications are not free. Okay, and sometimes we need lots of communications. Communication means number of bits being exchanged between two parties. Okay? So communications, amount of communication is very, very important for efficiency. Okay? And in some other cases, information leaking is very important. Very important. Because this is really connected to the security of the computation. So information leaking is very, very important. The goal is try to make leak of information as small as possible. Okay, that is very important. So that's why now probably you have some kind of feeling about contemporary algorithms. Of course, those kind of traditional issues still very important. But other than that, we have a couple of different issues which are very important in contemporary algorithms. Okay, good. So, number 5. Overview of the course. Okay, number 1. This is a warm-up. This is a warm-up. Okay, so I'll show you a couple of 2 or 3 basic techniques for design and analysis of algorithms. So this is a warm-up. So this is nothing to do, it's a little to do with contemporary algorithms, more like traditional algorithms. Okay? From number 2, we are really getting into contemporary new style of algorithms. The first one is online. Online algorithms, that is exactly, something like a stock trading. So online means input comes in online fashion, comes one after another, sequence of inputs. And you have to make a decision in each time. Okay, that is online algorithms, exactly stock trading problem. Number 3, approximation. Approximation algorithms, that is what I told you. It's, if it needs too much time for exact answer, then you have to give up. You have to give up exactly correct answer. And you have to be satisfied with the approximated answer. Okay. Randomization algorithm. Randomization, random numbers are very important for design and analysis of algorithms. Communication complexity That is exactly this thing. This is just to exchange number of bits between two parties and do some kind of computation by doing collaboration. As communication complexity means, just the number of bits exchanged between two parties. Interactive proof systems, that is again is done by two parties. In this case, it's quite similar to number 5, but in this case, the goal is to prove something, between, by doing communication between two parties. And this is also very interesting. I'll tell you when time comes. And more. And more. Okay, so this is a kind of a rough overview of this course. So as you see, the topics: online algorithms, processing algorithms, randomized algorithms, communication complexities, interactive proofs. Each of them, of course, each of them can be the whole course. Okay, the whole course of a graduate school. So if you go to, for example, MIT, Princeton, then usually they have many graduate courses, and some of them exactly about randomized algorithms, maybe even 2 courses for randomized algorithms. 2 whole courses for randomized algorithms, or maybe 1 whole courses of online algorithms, and so on and so forth. Okay, I'm trying to give you, all those topics, in just 1 course. So, you are very happy about that. Okay, good. So that is, some kind of introduction to the course. Any questions? Now, after, from now on, I'm getting down to real business. Okay, good. Oh, actually, I said that I'm going slowly, but just concentrate on the class, what I'm talking. If you're really waking up, then it's totally okay. You can follow me, but you are sleeping. It's of course totally impossible to follow me. So just concentrate on this class for 90 minutes, or maybe a bit less than 90 minutes. Then I think you'd be pretty happy about the course. Okay, now let's go to the real thing. Okay. Okay. So now, basic techniques for design and analysis of algorithms. I'll show you three basic techniques. Divide and conquer. Divide and conquer. And number 2, DP. Number 3, yes, backtrack. And local search. Okay. So this is 3 basic techniques I want to talk to you. Today, the number 1, divide and conquer. This is the most basic algorithm technique. So I think this is very important to know this technique. Or if you already know the technique, then it's very easy, again important to review what's the idea of a divide and conquer. Okay, the idea is very simple. Okay, now here, idea is very simple. We are given a problem. Then what we do is just reduce its size. Okay. We're given a problem of maybe size 100, the problem 100 numbers. Then we just try to reduce the size of the input from 100 numbers to 50. Okay, that is the basic idea. It's pretty easy. So I'll show you 3 examples of this technique. The first example, I'll show you 2 examples today, and the last one next week. I'll show you 3 examples why divide and conquer is very, very strong for design and analysis of algorithms. So example 1. This is a very famous problem that is called the counterfeit coin problem. So given n coins, they all seem the same, looking same, all looking same. Exactly 1 fake coins. Exactly 1 fake coin with a different weight. Different weight. Okay. So your job, your problem, of course, find fake coin using balance scale. What is balance scale? Balance scale is looks like this. Okay, so if you put coins to pounds, then of course the weights are the same. Then the pounds are balanced. Okay? The weights are different. Then pounds are tilted. Okay? So this is balance scale. Everyone knows this. Okay. I have one assumption. To make things simpler, I have one assumption. Okay. The outcome of this balance scale is just 1 bit, 0 or 1. Okay, just 1 bit. So outcome is 0 or 1. Maybe yes or no, or balance or tilted. So you can get only one bit information from the balance. That means when the balance tilted, you don't get any information which side is heavier than the other. So this unbalance or this unbalance, you don't know. Okay? So that's why I'm saying that the output only one bit, 0 or 1. Balanced or tilted, balanced or tilted. Okay? Your goal, of course, minimize. Okay, number of the times. Of course, minimize the number of times of using balance scale. Okay, so this is a kind of a normal, very natural goal. Okay, so do you understand the problem? Okay, I'll show you a simple example. Okay, we have 4 coins. 1, 2, 3, 4. Okay. And we know exactly 1 coin is fake with different weight. Now, what would you do? What would you do? Try to find the fake coin. That's pretty easy. Okay. I do first. I take number 1 and number 2 coin. Number 1, number 2 coin, I put them onto the pans. Onto the pans. Number 1. Number 1 coin, number 2 coin. Okay? Then the outcome is balanced or tilted. Balanced or tilted. If the scale is balanced, then what would you know? Of course, 1 and 2 coins are true coins. Okay? So, in that case, what would you do next? Next, I put 1 and 3 on the pans. Okay? And I already know that this is correct. This is not fake. Okay? This is not fake. It's okay. Okay? So, then balance or tilted. If it's balanced, then 3 is also okay. Then what is a fake coin? Of course, number 4. The answer. And this is number 3. If it's tilted, then this coin is okay. Then this one should be fake. Right? Okay. What about this case? What about this case? This case, I would again put 1 and 3. 1 and 3 on the pans. Now, we know, okay, so, yeah, now this is tilted. Tilted. That means 1 or 2 must be fake, right? 1 or 2 must be fake, because we know that exactly 1 coin is a fake. That means 1 or 2 must be fake. That means 3 and 4 are okay. Okay, 3 and 4 are true coins. So number 3 is okay. Good coin. Now, balanced, tilted. If it's balanced, then 1 is also okay. That means 2 is bad. 2 is bad. Okay? And 1 is bad. So, it is how many times? do you need to use scalings? Twice. Okay? Once and twice. Once and twice. So, two scale. For 4 coins. Okay? And if you think a little bit, then this is optimal. This is optimal. Okay? It is impossible to find fake coins using just once, balance scale once. It is impossible by using scale balance once. Impossible. Okay. Now we have 8 coins. What is algorithm? If you have some difficulty of seeing blackboards, blocked by our camera, then why don't you move to some other places? Yeah, please. Yeah. Okay. So what would you do for 8 coins? What is your first action? Do you have any idea? Please. You what? I'm sorry? Oh, you put the half of the size. Oh, of course. No. I'm asking a concrete action. Of course, it's a size. That is your goal. But how would you do? How would you do for that goal? So which coins should be on the pants? That is my question.
Can you put 4 coins on each?
Okay, 4 coins on the left side and 4 coins on the right side. Then it always tilted. No information.
Can you put like a set of 4, so 2, 2?
Yes, exactly. How to write it? How to write it? I don't know. Okay. So 1, 2 should go to the left side, and 3, 4 to the right side. Okay. So this should be your first action. Or of course, the number of coins. Which coins are not so important? 2 coins to the left, 2 coins to the right. Okay, that should be your first action. Then balanced and tilted. Then what would you know? If the scale is balanced, then there is no fake coins in this group. That means the next the fake coin should be 4. No. 5, 6, 7, 8. So you should try to find the fake coin from this group, right? If it's tilted, then of course the fake coin should be here. That means your problem is 1, 2, 3, 4. Okay? So by using balance scale once, then you can make the size of the problem from 8 to 4. Okay? This is the idea of divide and conquer. The idea is very simple. Just try to reduce the size of the problem by doing something. Okay? What that means? So now we have n coins. N coins. N coins. Then what is and Tn, T of n, number of scalings for finding fake coin from n coins. Okay, then T of n can be written T of n over 2 plus 1. Why? Because by using the balance scale just once, you can reduce the size of the problem from n to n over 2. Okay? So that is a recursion. Now, this is, of course, T n over 4 plus 1 or 2 and log n. And so this is a complexity. This is the complexity of this problem. Okay. Actually, you know that at the last moment, you need to use this fact. When the number of coins becomes 4, okay, now it's you need two. You need two scalings. You need two scalings. At the last moment, you need to use this fact, but basically it's pretty easy. Okay. Any question? Good. Now example 2. Example 2. We are given numbers, maybe n integers. You know, this is not so important. N integers. Problem. Oh, I'm sorry. Numbers and integer k, and also n numbers and integer k. Find find the kth smallest number during the given n numbers. And our goal is also very standard, minimize the computation time. So this is a standard goal, very standard goal. So I'll show you an example. For example, k is equal to 5, and the number n numbers is 7, 2, 12, 5, 15, 3, 8, and 6. Okay, so we have 8 numbers, and we like to find the fifth smallest number. What is the answer? 1, 2, so 2, 3, 5, 2, 3, 5, 6, 7, 8, 12, 15. Okay, so our answer 1, 2, 3, 4, 5. Okay, so our answer is 7. Our answer is 7. Okay. Of course, we are given number that is not sorted, kind of a random order. random order. Of course, of course. What's a very, easy problem? A very easy problem. Okay. So trivial solution. Trivial solution is, just a sort. Just sort the numbers, exactly as I did here. If you sort the numbers, then after that, the answer is obvious. The answer is obvious. Okay. So the trivial solution is to sort the numbers. But this is not so good because then you need order n log n time. Actually, this is not order, but I would say this is theta. Well, this is not so important, but n log n is optimal. So if you use sorting, then your computation time should not be less than n log n. N log n. Okay. But of course, you notice that we don't have to be sorting. If you do sorting, then you can get the third smallest, fifth smallest, sixth smallest. You can get the answer for all k. But what you are required now is only 1k. Okay, only 1k. You need a fifth largest. You don't need a sixth largest or third largest or second largest. Okay, that means doing sorting is too much. Right? It's too much. So our goal is more efficient, faster algorithms. Actually, a little bit surprisingly, we can do this in linear time. In linear time. Linear time means it's a little bit surprising. So suppose that you are 1 million numbers, huge numbers, 1 million numbers, and you want to find, 335,6,122 smallest number. Okay, it's a huge number, and you know exactly this number. You can do this just scanning a couple of times. Okay, that means, linear time means just scanning the whole. Okay, it's a huge, this lots of numbers, maybe 1 million, and you'd like to this one, this number. Of course, it's not sorted. It's completely random. Okay, then, I show you, we can find this number, 735,000 or 6,020 20-second number in linear time. Linear time means, 3 times n or 4 times n or maybe 5 times n. That means just scanning 5 times. Just scanning 5 times, then you can get this number. It's unbelievable, right? Completely random. Okay. This is also find of S and K. S is a set of the numbers. S is a set of numbers, and the K is the case largest. Okay. suppose that we can find okay. Suppose that we can find an approximately middle number A quickly. What do I mean by approximately middle? Approximately middle is simple. So suppose this is a whole number. And suppose that it is sorted. So minimum, this is minimum number, the maximum. I'm saying that we don't sort. We don't sort the number, but suppose that the number is sorted. Then approximately middle means something like this. So 1/3, 1/3, 1/3, and the number belongs here. Okay. So I would say this number A is approximately middle if it belongs to this area. That means there is at least 1/3 numbers smaller than A and at least 1/3 numbers larger than A. Then I would say this is approximately middle. Clear? Good. Now, here's our goals. Very easy. Number 1, obtain A. How to do that? Of course, that is important. But I'll tell you in a moment how to do that. But suppose that we can obtain A magically. Okay? Number 2, just scan the whole number, then divide the n numbers into 2 groups, less than A or larger than A. Okay? At most. So scan the whole number, divide the whole number into 2 groups, larger than A group, at most smaller than or equal to A group. Now, call find S prime, K prime. Okay. Of course, the question is what is S prime and K prime? What is S prime and K prime? Let's see. Maybe I'll use that example. Then, okay. Suppose that A is equal to 5. A is equal to 5. Then this group is 6, 7, 8, 12, 15. A equal to 5. This group is 2, 3, 5. Okay? So suppose that A is equal to 5. 5 is yes, it seems like approximately middle. Okay? And if A is equal to 5, then this group is 6, 7, 8, 15, and this is 2, 3, 5. Okay. Now, what is the goal? Our goal is fifth, fifth largest. Fifth largest. Then, which Which group has this number? Of course, this one. Okay? And in this group, what is the value of k prime? That is 2. Because this we have 5 and 3, 5 minus 3. Okay? So k prime is equal to 2. Yeah, that is 5 minus 3. So it's very easy to calculate k prime, and s prime is equal to 6, 7, 15. Okay? Is that clear? So s prime and computation s prime and k prime is, just the elementary school mathematics. Good. Okay. Now, again, Tn is a computation time for n integers. That is T of I would say this is not yeah. Okay, cool. 2000 plus some constant c times n. Why? Because this, as I said, the size becomes the size of s prime, and s prime is at most 2/3. Why? Because you are assuming that a is approximately middle. Approximately middle means, this set s prime should be this part or this part. Okay, I'm sorry, this part or this part. Okay, that is at least, at most 2/3 of n. Right? So this is at most 2/3. Maybe this might be an inequality, but and what is Cn? This is a computation time of number 1 to 2. Step number 1 and step number 2. This is obviously linear in n. Maybe n, just n, not c is equal to 1. So maybe n. Okay, but because just scanning, scanning the whole number once. Okay, so this is just n. Then this is a what? Right? This is a geometric sequence. It converges. So this is a linear n. Actually, I don't know. This is coefficient is pretty small. Okay, just linear. We are done. We are done. Okay. Now, of course, the question is how to here. The question is here. How to obtain a? Okay, the easiest way is to pick some number at random. Then with high probability, it should be approximately middle. But we can do that deterministically without using any randomization, as follows. Okay. So now, how to find, how to obtain? How to obtain approximately middle number A? Okay. Not coin. Coins are finished. Okay. We divide the whole numbers into groups. N over 5 groups of 5 coins. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. Maybe you have some remainder here, but maybe it's not so important. Okay. So suppose for simplicity, suppose that the number n is visible by 5. Okay. So you have these groups. So just easy. This is first 5 numbers, second 5 numbers, third 5 numbers, and so on and so forth. Okay, divide the whole numbers into groups of 5 numbers. Okay, then number 2, we sort them. Sort 5 numbers, each 5 numbers. So small, large. We sort each 5 numbers within that group. Okay? You can use any sorting algorithms because this is pretty easy. What you do is just sorting 5 numbers. You can use any sorting algorithms. Okay? Then you look at these numbers. Okay, these numbers means the middle one, medians of each group. Okay. So we have n over 5 numbers. And find the median of these numbers. So n over 10, smallest one. Okay? How can we do that? Of course, we can use recursion, right? We can use find. Algorithm find. Okay. So now here we have A. Okay. So once again, we have n numbers. Okay. So divide into these groups, and then sort each group. Then just look at these n over 5 numbers and obtain the median. Okay. So now I'm claiming that this A is indeed approximately minimum. Approximately middle. I'm claiming. Why? It's pretty easy. look at these groups, and look at these groups. Okay? So, suppose that number here, then, the number getting larger this direction and larger in this direction. Oh, I'm sorry. I forgot very important one thing. We need, I'm sorry, that's fine. This is okay. So this is a middle, and suppose that this is smaller, okay, small. This is large. We don't do sorting. Against this, these numbers, but suppose that we would have sorted. Suppose that we would have sorted. Then, this is a small number, and this is a large number. Then, this direction is getting larger, and this is getting larger. So that means this number is larger than here, larger than A. Similarly, look at here. Okay, look at here. Then this is larger and larger. That means this number is smaller than A. Okay? So that means we have at least n over 4 numbers it's an A and n over 4 numbers are larger than A. That is actually the definition of approximately middle. Well, in the previous definition, I used 1/3, 1/4, but that's a small difference. Okay. So A is indeed approximately middle. We are done. So now we finally compute computation time. T of n is equal to T of n over 5. Why? Because we need to obtain this number A. Okay. Why n over 5? Because this group, the sequence of this number is just n over 5. Okay. And we there's a case k prime, I don't know. So find S2 prime and k prime. K prime is equal to n over 10, and the size of S2 prime is 1/5 of S. Okay, that's fine. We have T n over 5 plus T of 3/4 of n. Why? Because this is a recursion step. Right now, previously, this is S prime is at least, at most, 2/3. But now we have this property. Because of this property, this is at most 3/4. And plus Cn, linear. This Cn means all other computations. For example, this part and that part. Okay, that part. Well, you can understand why this is linear, because it's just sorting 5 numbers are pretty easy. So of course it may be 10 steps. Okay, sorting 5 numbers needs 10 steps. Okay, and dividing numbers into groups also obviously needs maybe n or 2n steps. That's fine. That's enough. Okay, so the c is a small constant, something like a 2 or 3. Okay? Now solving this equation, then what? 20 cn. If you're not sure, then just substitute this 20 cn into this equation, then everything's fine. Okay? This is 20c is constant equal linear. Okay, 20c might be a little bit too big, but of course you can optimize this algorithm by doing some details. Then you can reduce this constant much smaller. Yeah, something like I don't remember, but I think the best possible might be something like a 5, 6, 7. I don't remember, but this constant should be much smaller. That is what I said. What I told you previously. Just scanning the whole number 5 or 6 times, then you can get exactly your target for any size of the input. It's really amazing. Actually, this algorithm was found. I don't remember. It's something like 40 years ago, but at the time, this is a big news, very big news, because at the time people didn't believe that this job can be done in linear time. It's really big news. Yeah. Okay, so that is I showed 2 examples of divide and conquer, and in the next class, next week, I'll show the third example. That is today just what we did is just reduce the problem size from n to something smaller than n, something like n over 2, n over 3. Just we can reduce the problem size, but that is divide part, and actually we need conquer part. And in today's 2 example, we didn't have a conquer part, a clear conquer part. So the third example, I'm going to talk to you next week, do have a very interesting conquer part. Okay, so I stop here. See you next week.